All right, let's talk about something truly mind-bending, quantum computing. This is a technology that's, well, it's not just a faster computer, it's a completely different way of thinking about computation itself. It promises to tackle problems that our most powerful supercomputers today wouldn't even know where to begin, and it does it by harnessing the seriously weird rules of the quantum world.
Okay, so to get this, you have to start with the absolute basics. Everything you use, your phone, your laptop, it all runs on bits. And a bit is basically just a light switch. It's either off, which we call 0, or it's on, which we call 1. Super simple, right? Well, a quantum computer throws that right out the window. It uses something called a qubit. And the best way to think about a qubit is like a spinning coin. You see, while it's spinning, it's not heads or tails, it's kind of both at the same time. And that one little crazy difference? Yeah, that changes absolutely everything.
So how exactly does a spinning coin give us, well, superpowers? Because that's really what we're talking about here. These are the fundamental quantum rules that make this whole thing work.
First up is superposition. That's the fancy name for our spinning coin. The fact that a qubit can be a 0 and a 1 at the same time is huge. Think about it. If you have just a handful of these qubits, the number of possibilities they can explore all at once just explodes. It's not one path at a time, it's a whole universe of paths all at the same moment. All right, if you thought superposition was weird, get ready for entanglement. This is where things get, well, downright strange. You can link two qubits together in this special way, so they become a single system. And the crazy part is, no matter how far apart you pull them, I'm talking opposite ends of the universe, what you do to one instantly affects the other. Instantly. Even Einstein couldn't quite wrap his head around this one. He famously called it spooky action at a distance. And you can see why, right? It feels like it breaks the rules. Nothing is supposed to travel faster than light. But this connection, it's just there. It's instantaneous. And while it's bizarre, this spooky link is actually one of the most powerful tools we have for quantum computing. So we've got these incredible qubits that exist in multiple states and are spookily linked together. It sounds like we're all set, right? Well, not quite. There's one giant catch. The second you try to actually look at the qubit to see what it's doing, the quantum magic just vanishes.
The moment you measure it, that spinning coin is forced to land. It has to pick a side. It collapses, as they say, into a good old-fashioned 0 or 1. So, here's the key takeaway. The process is quantum, exploring all those possibilities at once. But the answer you get at the end? It's always a classical bit, a simple 0 or 1. Pulled out of that sea of quantum probabilities.
Okay, so if these things are so delicate that just looking at them breaks them, how in the world do you build a computer out of them? How do you actually control these superpowers to get a useful answer?
Well, believe it or not, people are actually building these things. Qubits aren't just a concept on a whiteboard. They're real, physical devices. We're talking about things like tiny electrical circuits chilled to temperatures colder than the darkest vacuum of space, or literally trapping individual atoms in place and poking them with lasers. This is serious, high-precision, next-level engineering. And controlling them? It's kind of like a regular computer, but on a whole other level. You know how a normal computer has logic gates, things like and, or, not, that flip bits around? Well, quantum computers have quantum gates, but instead of just flipping a 1 to a 0, these gates do things that sound like science fiction. You've got gates that can kick a qubit into superposition, start the coin spinning, and other gates that can create that spooky entanglement between them. So when you put it all together, every quantum calculation follows the same basic steps. It's like a little dance. First, you get all your qubits lined up and set them to 0. Then, use those quantum gates to get them all spinning and entangled. That's the superposition part. Next comes the actual computation, where you apply more gates to manipulate their states. And then finally, for the grand finale, you measure them, they all collapse, and you get your answer.
I know. This sounds ridiculously complicated. So you've got to be asking, why bother? Well, the reason we go through all this trouble is because of the kinds of problems quantum computers can solve. We're talking about challenges that we literally thought were impossible to ever solve.
The real magic here is something called quantum parallelism. Here's the best way to picture it. Imagine a giant maze. A classical computer, even a supercomputer, has to try each path, one by one. It hits the dead end, goes back, tries another. A quantum computer, because of superposition, gets to explore every single path in the maze at the exact same time. It's not just faster, it's a fundamentally different way of problem solving. And this ability to look at everything at once makes them insanely good at very specific, very hard problems. For example, breaking modern encryption, which relies on the fact that it's impossible for normal computers to factor huge numbers, or simulating molecules to design new medicines from the ground up, or even solving mind-boggling logistical puzzles, like figuring out the absolute best route for an entire fleet of delivery trucks.
And this isn't just theory. We already have specific recipes, or algorithms, for these quantum computers. You've got Shor's algorithm, which is basically the ultimate code breaker. It's the one that has cybersecurity experts a little nervous. Then there's Grover's algorithm, which is like a super-powered search engine that can find a needle in a haystack way, way faster than any regular search. These aren't just guesses, they are mathematically proven to be faster.
Okay, so this all sounds amazing, like we're on the verge of a revolution. And we are, but we have to be real here. We're still at the very, very beginning of this journey, and there are some huge roadblocks ahead.
The biggest problem of all? Qubits are, well, they're divas. They are so incredibly sensitive. The slightest vibration, a tiny change in temperature, any little bit of noise from the outside world can make them forget their quantum and just collapse. This is called decoherence, and it's the #1 enemy of quantum computing. It causes errors and makes it incredibly difficult to build bigger and more powerful machines. But look, even with those massive challenges, the potential is just too big to ignore. That's why the race is on. Right now, people are developing new kinds of encryption that even a quantum computer can't break. They're using the early machines we have today to start designing new drugs, to build better financial models. The work is already happening. Because everyone knows that whoever cracks this will literally change the world.
So, it all comes back to that simple spinning coin, an idea that seems almost playful, but holds the key to solving some of the biggest, hardest problems humanity has ever faced, which really only leaves one final question for you. If you had a quantum computer that could solve almost anything, what would you ask it to solve first?